All right, ladies and gentlemen, as you already know, and you're not, some of you aren't too happy about it, roadmaps are going to become an important part of your life. So you've got this thing on a test, and you don't know where to start. So I usually try to help you with that. Where do you start? Start here. And this reaction we did today, it's not that old, but we also did it earlier because it's an acid-base reaction. You're going to get NH3. It's not worth any points. I'm going to sneak it in down here, plus NH3. So where did it get that H from? The alkyne, yeah. So HC, triple C, here's box D for you. The anion of acetylene. Oh, that's new too. New. UPAC. Oh, we're out of paper. Yeah, you guys got it. UPAC is ethine. Old. No, it's not new or old. Forget it. This you have to learn, and it's a travesty actually. Its name has mistakes in it. What? Acetyl in organic chemistry is not anything to do with that molecule. And it's one of the most common units in biochemistry, acetyl. This is an exception to that. There are videos on why it's an exception. There's a page in the textbook about why it's an exception. It talks about the history of how the molecule called acetylene was discovered and what they made it into. And then that had an acetyl group in it, so they named it like son of acetyl. You know, like you get bin as a prefix in the Arabic and whatever follows, it means son of, right? Or if you're Scottish, it's Mc. McDonald means son of Donald. Maybe you didn't know that. So it's named after like what it became, or sometimes you're named after where you come from, okay? And acetylene has that history. So we just go with that. Because an acetyl is a carbonyl that has a CH3. All other acetyls in your future are going to look like this. Wow. Get excited. The computer can't keep up. Your pen becomes an eraser. We got a lot going on here. So that's why I don't like the name, but we have to live with history. That is the normal acetyl unit in organic chemistry. We're going to do a reaction later on this page that converts this to a carbonyl with a CH3, and you'll see, oh, well, that was the reaction that they used to name it. Right now, just acid base. Now we have to learn that acetylene is this picture, not any other picture. And I could ask for KEQ. I could, but I didn't. It would be 25 minus 40, negative 15. This is a nucleophile that can be used with synthesis. What kind of molecules do you have to react it with for synthesis? A carbon with a halogen. A carbon hexane with a halogen on carbon 3. My new bond's going to be to carbon 3. It's not going to be R when I'm done, though. It's going to be S, because there's a backside attack with a stereochemical inversion. Oh, wow, that sounds fancy. Okay, do you want to do the bottom one first? Why not? Do the hard one first. HC triple C has a new exciting bond to hexane. Third carbon of hexane. Put the H on. You need to make it S. Right now, it is S. If I do dash and wedge. There you go. That's exciting. Just a reminder, it's now S. Upstairs is easy. What's the group that's going to be in green on the box that I labeled A? Is that right? A. I want to see both of them. You're going to have your HC triple C still. Exciting new bond, but what's the group attached this time? CH3. Yeah, not as exciting. I correct myself. It's equally exciting. You made a carbon-carbon bond. Let's tackle these new reactions. I mean, based on chapter 6, you would predict this. Based on chapter 6, we learned the mercury with water. I know this is a slightly different mercury, but it's still mercury 2+. It's still making a triangle. It's still getting a backside attack using water on the triangle. You're going to end up with an OH on the carbon, on the opposite side of the double bond as the mercury. So this is your prediction based on chapter 6. In black, on the more substituted carbon, OH. On the less substituted carbon, Hg. And a CH3 up here. But what you don't know right now, two things you don't know right now. One thing you don't know, this is an enol. Good name. I love when we have good names. It's got everything it says in the name, doesn't it? Enols are subject to tautomerization. Oh, we have some nice words in this course. Tautomerization. A reaction where an H moves, 2, a pi moves. You want to see that? There is the single bond. Here's the O. Where's the H? It's now here. Okay. Where's the Hg? I would like to point out there was an old H on the black carbon already. That's why it's black. And Hg plus. Oh, that's not going to go in the box though. Subject to new conditions. And there's your pi. And you're still not done because you don't know fact number 2 that you don't know yet. I totally messed up. Now, totally is a harsh word. My box is not making me happy. Yeah. I don't have the methyl on there because I flipped things the way they're supposed to be. I'm kind of lost what to do next, but I'm going to get it back. Black carbon. I should have done it this way in the first place. Single bond. Okay? Enol's highlighted up there. CH3 is up here. This is better now. Mercury's still up here. The pi bond is now over here is where I went wrong. Wait, the mercury's not there. Mercury's here. This is the mercury one? No, I'm happy with my original. Sorry. There we go. It's fixed. It was there all along. So would you predict the O on the more substituted carbon based on chapter 6? Remember, you made a triangle. Anytime you make a triangle, the next step is a backside attack on the more substituted carbon. Yes, you put the O in the more substituted carbon. You would have predicted an enol, but enols don't like being enols. They undergo tautomerization to this. Guys, I had everything I needed here. My goodness. Okay, good. A reaction where an H moves, so did the H move? This is 1. 1 gets you here. 2. CHG plus undergoes with this molecule. Oh, sorry. With this molecule, Hg plus attached to C. What did I do? Not having a good day here. Things aren't working. Okay, gonna react that with sulfuric acid. HOSO3H, there we go. And water. Okay, and what you get is CH plus Hg2 plus with a little feline noise. Why do we have that little feline noise? Catalyst is back. Reaction's called protonolysis. Oh yeah, you have to know protonolysis. And Monday we're going to do the mechanisms too. You'll see the mechanism of protonolysis. Protonolysis is what it says. I love words that are what they say. It's one of my favorite words, favorite word types, called a portmanteau, where you've taken 2 words and glued them together. What language on this planet is the most commonly used, are portmanteaus most commonly used in? And they don't stop at 2 words. They often go to 3, 4, 5. And they get words like the Berteskund, words like that. It's the Germans. They do portmanteaus better than anybody, okay? I love them. They got more meaning than their individual words. Proton was used to do what? Proton was used to do what? Look at the word, it's in red. No, it doesn't follow by protonation. Proton was used to do what? Lyse. What's a lyse? Cutting. Learn. For not just this class. You're going to hear it in many classes. Lysing. It's breaking apart. Yes, we cut it apart. We got the carbon away from the mercury. It became carbon to hydrogen. And mercury 2 plus. So what's your quick fix to get to the second thing here? I'm going to do an erase and a replace. What do I have to fix? The mercury is now going to become what? The mercury became H. That's an easy fix. Yeah, there you go. Do you want me to make sure you know where that came from? I'll do H2SO4 in purple. And change that to, oh, we already have a purple H. You get 2 new purple H's, that is true. On Monday, when we do the mechanism, you'll see why. They're both purple. Okay, give you something to wait for. Good stuff. Okay, so what did we get? We got a ketone. Guys, don't take this for granted. You just learned how to make a ketone. Anytime you learn how to make one of your functional groups, you should be very interested. In your mind, you have to get a list going of reactions that make each of the functional groups. That's your goal. By the end of Chem 242, have reactions that make every functional group and have reactions of every functional group. We learn it first that way because we break organic chemistry down to functional groups and how they react. But later on, you got to remember, oh, we also learned reactions that made these functional groups, and it's all interrelated. And that's what they like best about organic chemistry as a prereq for health careers. Things leading to other things, that's medicine. Okay, well, that level of thinking is the same in natural organic chemistry, especially synthesis. Okay, now this next one is good to learn right beside this one. Based on chapter 6, you would have predicted this. Here's your C, double C, and in this reaction, you get a syn addition of B with whatever Sia is. You don't even need to know. Not yet. You will need to know. And you got a syn addition of that and H. And the old methyl turned color to blue. That's step 1. And then 2 takes the same thing and makes an OH there. And you just learned what that's called. I'm going to highlight it. And you tell me what it's called. Because I have the same highlighter on another version of that functional group. It's an enol. And you know, enols don't like staying enol. What would they rather do? They are subject to tautomerization. So let's see if you can tell me what goes in the box based on this. H moves, pi moves. Well, here it is. H moved from the alcohol to the position, not the carbon attached to the alcohol, but one away. H is going to move from the alcohol to not the carbon attached to the alcohol, but one away. You with me so far? What happens to the C single bond to O? Double bond to O. Okay, so I got my C single bond to O becoming C double bond to O. I got my C single bond becoming a double bond. There's the pi switch, went from here to there. And the H that used to be blue is now here. We had an old green H there from our hydroboration, and we had a blue methyl, which was formerly a green methyl. And that is not a ketone. What is that? You have just learned a way to make aldehyde. Aldehydes and ketones. Top of the screen. From what particular type of alkyne? The one that's on the end of a chain. Sorry, say it again. On the end of a chain? Terminal, that's right. So you can make terminal alkynes into either ketones I'm going to just do this and erase it. With an acetyl, it will always be an acetyl. Okay? Well, that's not the acetyl I should have circled. Do you agree this is also acetyl this direction? The methyl, it was there from the beginning. It's not like it's a new deal. That is an acetyl. This explains why acetylene got its name. I know this is not acetylene anymore, but the same reaction happens with acetylene, and you get an acetyl. That's where it got its name. Okay? Acetylene has acetyl in it. Okay? That acetyl wasn't here, was it? Okay, I won't erase it, I'll leave it. No, I'm going to erase it, because you're going to think that's the end all be all. You didn't make an acetyl here, you made it just an aldehyde. So, terminal alkyne, that's going to become the carbonyl with these chemicals. Terminal alkyne, the other carbon is going to be the carbonyl going this direction with these chemicals. There are 3 chemicals there, people. There are 3 chemicals there. Water is just as important as the other 2. Leave the water out and find out. Minus 0.5. Okay. 3 chemicals here, but you have to break it down to steps. If you leave the steps out, minus 0.25. If you put chemical 1, chemical 2, chemical 3, no numbers, you're losing a quarter point. Why? Because if you do mix those 3 together, I want to know ahead of time so I can leave the building. They will explode. you need to form a full hydroborated intermediate first, which is here, so that the dangerous BH bond doesn't interact with this. Okay? It will go very squirrely if you react this with this. So make sure this is gone, and it became this. Step 1 made this, and then step 2 makes that. Okay, so yeah, when I put numbers, they're serious. They're not just random. No numbers here because all 3 are together at once. There's no numbers. Please don't put numbers there. Minus 0.25.
Professor, have you reacted to all of these in person?
I've done most of these in person. Yes, not all of it. No. Okay. So where are we going next? Oh, we got to go from here. We did. Time's ticking. We've got this guy. Now you got to show that you know what we just learned. How do you do this synthesis? This is a new synthesis right here. This bond did not exist. Oh, wait, that did exist. This bond did not exist. You agree? That CH2 phenyl is nowhere to be found here. So how did you make this bond exist is the question. What did you do first? Remember, you started here. You made C-triple-C first. What kind of reaction was it? She's gone. I was going to point to the person that said the same answer before, and I did, and she's not there. Acid base. She picked up the slack. Okay. You got to do an acid base first, but this time you're going to do it on this molecule. Do you agree there's still a 25 pKa present? You want to use the same base because memorizing new bases is not necessary? So base says step 1, KNH2. So you've made this molecule into something that has a minus here and the rest the same. Minus over here, the rest the same. Acid base, the proton got removed. I need that minus to attack this carbon in a new molecule. And what must be on this carbon for an SN2 to happen? A electronegative, pick one of the 3 halogens that's not fluorine. Bromo's good one every time if you want. Okay, I need a phenyl, CH2, bromo. Step 2. Bromo, CH2, phenyl. Acid base followed by synthesis. Okay, and you got your new bond. You're very excited. And then you're going to learn 3 reactions with internal alkyne. Yep. Do you know how to make acetylene into a terminal alkyne? Right there. You know how to make acetylene into an internal alkyne? Takes more steps, right? But basically the same steps. And now you're going to learn that these are all reductions. And I think you know the H2PT one. The pi gets, each pi gets a new bond from C to H. And you're going to do it twice because you got 2 pi. 2 pi. 2 pi. 0 pi. Oh, I can't lie. Phenyl has pi too, right? Phenyl doesn't react in this course. Phenyl does not react in this course. You will learn lots of phenyl reactions in Chem 242. They are very important, but we're not going to do that till Chem 242. And they're not easy to do. Under the conditions in Chem 241, this will not react. So when I'm saying there's 2 pi bonds, I'm only talking about these 2, right? Not the 3 in phenyl. Okay, so you're going to go phenyl, CH2 once, CH2 twice, CH2 3 times, CH2 4 times, C, stereo. There you go. You want to see the 4 new H's? I mean, you don't have to, but here they are. Started up here. There they are, right? And you call that hydrogenation, right? Well, this one over here, also hydrogenation. But this catalyst, there's your hydrogen for hydrogenation. Your catalyst, it's called Lindlar's catalyst. That's a name I'm not a big fan. There's no hydrogen in Lindlar's catalyst. So if you put Lindlar's catalyst over an arrow, you'll get partial credit, that's it. If you write H2 in Lindlar's catalyst, then you'll get your full credit. And the only thing you need to remember now is that combination only reacts with alkyne. It does not touch alkene. The lead sulfate at the end there is like, we call it a poison. And what it does is it like turns down the reactivity of the catalyst just a hair. And the one with the 2 pi bonds is just reactive enough. And the one with the 1 pi bond is not reactive enough. And H2, the last thing we did last day, thin or anti. Remember, we had a chunk of platinum metal. That was the evening notes, but we did actually show the mechanism in the evening. Piece of platinum metal where the alkene comes in on it. Don't the H's have to come from the same side? Because the H's are sticking off the platinum metal. They got to be thin. And it is. So I want a cis alkene with H's on the same side. So that's a good reaction. And I'll put the H's in blue. Copy everything else like I see it. That didn't change. 1, 2, 3. 1, 2, 3. Third was phenol. And time is ticking. All you need to know about that other combination to the left is it does exactly the same thing as H2 and Lindlar's catalyst. Different way to accomplish the same objective. So you don't have to, you could write F and E are the same. Advantages of Lindlar's catalyst. It's a catalyst. You use it and you can reuse it every time for years. Disadvantage, real expensive. But in industry, we don't care about expense. If it's an expensive catalyst, you buy it one time, you can actually write it off in this fine country we have. And capital outlay purchases, if you make big ones, you can write them off if you're smart. And there you go. So the disadvantage is it's expensive. So these are cheap. They're cheap. It's a messier reaction. Catalysts are real nice. You can just filter them away. It's messier, gives lower yield, but you get the results and you can afford it. All right, we're almost done. That's not about a blank anymore. So what seems to be missing? We have ways of making cis alkenes, which are really valuable. You'll see in notes a lot of this going on, like triple dollar sign. And this guy he was like a single dollar sign. And then you get to, you know, the alkynes. These alkynes are like, I don't know, a couple bucks. But the real money is, you know, triple dollar signs. Yeah. Alkenes that have geometry are very valuable. Just like stereo centers are also valuable. Yeah, making stereo centers, doing it under control, so you know exactly what stereo center you have, very valuable stuff.
Now they make diamonds in glass.
Oh yeah. Oh yeah, we got the technology for making diamonds from coal. Okay, sodium and ammonia is the one that gives you the trans version of these two. So Na and NH3, mechanism coming Monday. Here's your new H's. One's up, one's down. After that, copy everything you did before. And you're going to give me these boxes. 1, 2, 3. 1, 2, 3. And then up here, phenyl once, so CH2 once, CH2 twice, phenyl third one. And big picture, I just need all the boxes. A, B, C, D, F, G, H, I, J. That's the end.